Hi guys, welcome. Today is about Inspire. Inspire is a software which is targeted at a CAD engineer. Those guys deal with the question on how a part should look like. But also those guys, they know the initial design space requirements, meaning that where can material go and where's the assembly and where do we have to leave some space for functioning parts or something like that. So the CAD market is a lot bigger than the stress engineer market. But thing is that those different markets, those require different needs, or those have different needs. The stress engineer, those guys deal a lot with element quality on getting a real precise statement on whether a part is functioning well under the conditions or not. If stuff breaks, right? This is stress engineer. CAD engineer is more dealing with the question how this part should look like, what things to use, how to design it, right? And those guys don't really deal so much with element quality and don't want to, but they also could greatly profit from having a tool which just shows a glimpse, a first version, a hint to how a part should look like if optimized for structural performance. So this is the big question here. And I know, I'm sure you know all of this by now, but I want to do this video a bit of a comparison between two versions of Inspire. And the most recent one is 2021.1, and I'm comparing that to 2020.1.1. And yeah, they changed a lot, and I like the changes. But you have to be careful sometimes, because if you don't know how this works, it works different now. And I will show that to you so you can relax, grab a drink, and yeah, watch me walk you through this. We will be doing a smart topology optimization model and maybe cover also a little bit of the polynerbs, so the reconstruction feature in Inspire. But rather not so much targeted at a stress engineer. I will be not so much talking about constraints and optimization setup, but rather on how to use the software. All right, without further ado, let's jump into it. I've prepared two monitors for you. So first monitor is the most recent one. You see also the darker color one. And then we have the second monitor, which is the brighter one, which is the older version, 2020.1.1. Now, let's start. And the first thing I noticed, and which is really greatly satisfying for me, is see them implement planes properly, global planes, and axis and origin point when doing your sketches. So first of all, what you notice, maybe I will just give you a quick overview and where to find what, right? So you have ribbons. Ribbons here, like in all modern software, you know those ribbon style. So you have ribbons here. And you can even do your own ribbon, right? Name it some name, my ribbon. And then just drag some things here to that. And then you have it coupled together. So for user-defined workflows, where you know I just need this, you can bunch them all together and have that in your own ribbon. And yes, but the thing is, you have ribbons here, and this is the functionality, basically. Then you have your model browser and your property editor, which I would suggest you show all the time. This is showing you important information. If you don't see those right away, you can enable them by clicking on View and then Model Browser and Property Editor, or just pressing F2 and F3. This is also, and you also have a Python window here and stuff like that, right? So you can check that out via View. Now let's see. You have the ribbon geometry, and for the old version, which is over here, this was the starting point of creating a part. Because you have your sketch tools here. Click here, for example, create a rectangular this, and I will do it a 100 by 100 rectangular and make a C-clip out of it. Maybe you know the C-clip by now. Pretty simple, but also famous example for topology optimization, simple one. And this is done like this. Here, trim. So this is the shape, more or less. And this is how you do it. And in the old version, right? And right click and swiping to the left completes the action. And once again, and now you're here. And automatically in the pull window, you can select the surface, enter a value, and that makes you having a solid volume. Jumping over here, it's done not on the geometry ribbon anymore, but the sketch ribbon. They have a sketch ribbon, and that I love because you have a new sketch, right? And you see the planes. Cannot stress that high enough because I can see the origin point. I know where I'm doing my sketch to. So this is pretty cool. So I'm doing that as well here. So let's do a quick thing here. So here, you saw that. I just clicked it. Never minded about the dimensions. I can insert them here right afterwards and then change them. This is how it's done in the new version. So 100 by 100, that's okay. Then let's make the other one, which is here to here, and then a circle on top of it, which is this one. And then the trim button is here, and we trim until we get our shape. That seems good. Then right click and going to the left, right click, going to the left. We're here. We are not automatically in the pull menu, so geometry pull. Select the surface, 6, and right click, swiping to the left, and we're done. Then it was a bit fast, but I think I have some rather slow-paced tutorials also, where we will go through each step more slowly. But if something is, if that's a thing for you, just leave a comment and I will do more detail, more slowly paced tutorial as well. All right, now let's create the bearings, right? So I want to cut some holes in here, and this is also different. Let's make it accurate with the most recent one and just comparison, not so tidied up with the old version to show what's different. So I want to create a sketch now. So sketch, new sketch on this level, and I want to make some holes. So here's circle tool. Well, I think this is a far off. Let's just use this one, right? Okay. It's an easier one with the circle tool like this. So what should we choose? 7. And the same thing for here. Now, here's the first thing I want to show you. You see that it's snapping to the vertical alignment to the other circle, but it's not snapping anymore onto the grid. And I did not find a button which undoes that. Yeah, you have to just click that slightly off. And again, 7. And then work your stuff out with the dimensions, which is always a good idea, because then you know exactly if it's the right thing. So 15 is here, and I think 15 as well here. So this should be the same, right? But the other one, I'm not so sure. So the other one is large. Now change it back to 15 and you're done. So right click, swiping to the left gets you out of the dimension mode, and right click, swiping to the left gets you out of the sketch mode. Now you see, all right, you have a sketch here. Now comes the thing. You want to remove it, right? So geometry push pull. And in the old version, let me just quickly show that to you. In the old version, it was like this. So if I have a circle around here, also keep in mind this create new part. This is not there in the new version. We will come to talk about this later. I don't care about this thing too much. But if I do a push pull here, I can add volume here and subtract volume if I go onto the other side, right? Very intuitive, very fast, but it's not anymore like this in a new version. There's some reasons behind that, and we will talk about this in a minute, but let's see if I just do the same thing. You click on there, and then you have to first select what you want to do. And here's your create new part, and not on the sketch anymore. The thing is, let's say we will see it afterwards if we do some tool geometry here to partition the model here. We want to have a new part, right? And there we have to do a adding of a volume into the other direction. So we cannot simply say in this direction as removal only. And that's why they choose to go this way of having to create here a create part, right? If that's not entirely clear, it will get clear in a minute. So I want to select remove here and then drag it into the other. Oh, that was the wrong handle. Drag it here. Oh, is that the? No, it's not the right handle. This one is the right one. Drag it into the here. Now, if you do apply, this applies it, but oh no, the sketch is gone. Where's my second sketch? It's just hidden, and that's why I suggest that you always show your model browser and look at how this is not present information on here. So here is no sketch left, right? Here's just a part. All right, here you have the sketch and it's just hidden. So enable it once more and you have it available for you. And then you see, if I forget to choose the option of removing material, it will just add material. All right, so remove material, -17. Yeah, we don't need that much, but it will work. And right click to the left and you're done. So now comes the funny part. We want to partition our model. Partitioning takes place because you don't want to apply boundary conditions and forces onto your design space. And this is why we partition the model, because we want to have a bearing here and we don't want to have the optimizer remove material from the bearing, right? So we partition it here. Partition, and it already finds both holes. So we can also add options here, so find smaller, larger, and then just hit apply. 3 millimeters seems fine. We could change it here, but that seems okay. And on the check mark, we have partitioned our model. Now look, if I just right click and click design space here, you could see it more clearly. So the gray area will not get touched by the optimizer, but it is still there. So it's not, yeah, just 1 or 2 sentences about that. As a designer, you have your design space where material could be. Then you have non-design space, but in different flavors. First flavor is a non-design space and there should be no material. It's just the one where you cut out the material. Yeah, it's not a design space. But there's also non-design space where there is material, but there has to be material. This is what the bearings are. So here in the bearings, those are defined, those will be there, and those will never get removed. The same thing goes for the boundary, for the forces, which I want to apply here and here. So I want to cut it here, but we don't have a whole geometry where we could easily partition it. So we have to define it ourselves. So we go to sketch, right? Sketch, rectangular, onto this plane. I see. On the old version, I would now have to be sure to select create new part. But as this is done on the pole option, I will not have to do it right here. So I will just simply select here 5 by 10, for example. And the same thing here. Also notice it's not snapping anymore. So you have to define it slightly off that you see it and then work your way with dimensions. So here 5, and that seems okay. So right click, swipe, and now here you are with your sketch. And now if you select the sketch and go to push pull or sketch, you have to select it here. Now you can choose to create a new part. Now if you just dragging, sorry about that, you have to be careful where to, oops. Okay, it worked, but it has -7, right? And this will go away, I'm pretty sure. Yeah, this goes away. So you have to enable the sketch once more. And here select also create new part. Now you see that you have part 6 and 7. So part 1 is a design space, I suppose. Then part 4 and 5 are our bearings, and 6 and 7 is our tool geometry, which we will use to further partition our model. So how this is done is, you see here Boolean. And Boolean lets you partition your geometry with other tool geometry. It's pretty a good option to do this and pretty widely used. So intersect is the one we're looking for. Targets, that means the volume we want to be affected by. And tools is the tool geometry. So tool would be this and this. And we want to keep our targets. We don't want to remove that. Tools can be deleted. Now pressing OK, you see how this is partitioned. And for that to be able to do it like this, you have to be sure that you created a new part, because otherwise it would be the same part. And on the old version, just to reference, if you want to do it something similar like this, you would have to say it on the sketch, create a new part. And then whatever you are doing here, this will be a new part. So if you pull that, you see, even as I'm pulling into the other material, it was adding material. And this is a new part, as you can see here, part 2, part 1. All right, going back to the most recent one. So what do we see here? This is a design space. No, this should not be a design space. So this is correct. So part 1, the design space. Part 4, 5 are the bearings. Part 8 is our load application point. All right, now boundary conditions. So in this case, we are done with doing the geometry and we want to introduce the boundary conditions, which means we want to use bearings here and forces here. So, first thing which comes to mind is boundary conditions structure, right? So we have fasteners and joints. And fasteners, those are screws, and one is definitely applicable here, right? Click once to select the inner hole and then click twice. If you see the little screw icon, this is the one which completes the option. And this is a grounded bolt. So it will secure the bolt also in this direction, right? It will not fly away. So it's a grounded bolt. And degree of freedom is it can turn around this axis. Same thing goes with joints. And the second one I will model as a joint. And I will talk to you about that in a minute. So this is a grounded pin. And the only difference here between those two boundary conditions is that this is securing the model in this direction. It cannot fly away in Z direction. And this is just introducing the rotational degrees of freedom. So it's holding this thing in place in X and Y direction, but it can turn around Z direction, and it can also move in Z direction. So this is the proper way to set this up. One constraint which fully constrains the model that it does not fly away, and the other one is just securing the as it is, right? So just a pin. All right, now the load application, you can see here, forces, loads, pressures, moments. We will go with forces right here. We can either select an edge, which is not that much applicable, or a force, a surface. And in this case, we want to use a surface, so 100 newtons, or maybe let's put a little bit more. 1000 newtons here, and 1000 newtons here. Should be enough. And that's about it. This is our first load step. So we have forces, we have boundary conditions, and if we want to add another load step, this is also a very frequently asked thing. Then we can go to this list icon here. Then we can choose to add another load case, and then maybe add another force, for example, push something here, right? And then you can see here with the list that which is active, right? Force 3 is active only in load case 2, but joint and fastener should be also be active in the load case 2 to have a fully constrained model. But we will skip that here with just one load case and make just one run here. So I will delete also this force. And this is about it, right? One thing which I didn't cover here is materials. So we have our parts, and they are assigned steel as a standard material. If you want to have our own material, you can do this with going to the material browser here and also choose to add a own material. So use a defined material and put your values in here. So Young's module, Poisson ratio, density, yield stress for a safety factor, and alpha is heat transfer coefficient if you have something thermally thermal stresses and stuff like that. Yes, this is about it, and now I will just start my first analysis. Before going into the optimization, I will start my analyze, and you have the analyze button here on the structure, and then we press the play button here, and faster and more accurate, that will change the function, the order of the elements. I can't remember the English word for that. Yeah, it's the order of the. Just have this German word in mind. Yes, it's you have elements of different orders. Well, it's not CAD engineer stuff, but stress engineer. So second order elements are more accurate because they can just not only model constant strain, but strain with a slope. And more accurate fixes that, uses second order elements, and faster uses first order elements. Because this is a simple tutorial, we will use faster here. And element size, you can leave that auto here for your first run, and we run it here. If you ever were wondering where these files are stored, those are under the user profile. So you see here under this PC, documents, Altair 2021.1, Inspire, Analysis. Now this is the current date. Yes. So this is the file. Well, this is the folder where the files are put here. Now you can see here the out file. It's pretty interesting to see if something worked or something didn't work. If you have a warning or do some troubleshooting here. So you can see through here. See some values about the compliance stuff, interesting stuff. And also you can also use here the files to do a post-processing in Hyperview even, or to just look at the FEM deck, so the input deck. And yeah, but this is rather stress engineer stuff, not so much CAD engineer. All right, so we had our first run. Double click here, will show you the results, and you will see your displacement values. I'm not sure if this is the standard value, because I know I changed here something, because if you want to have it like this with a rainbow legend, then you want to go to File Preferences and then to, I think it's not Run Options. Is it? It is Run Options. Run Options, and then here you have for each and every output, which is here, you can choose the color bar. In this case, displacement is rainbow. And I like the rainbow. So displacement or von Mises stress, for example, you can see here. Now, if you want to show the elements, because maybe stress engineer asks you to do this, just simply here, click here once, you can see it here. Now, if you want to, for example, make a final mesh here, this is also possible, but a little bit hidden. It is, I will go back to the part, so you see your results. Yeah, you're in this analysis box, and as soon as you're not in there anymore, you're back into the original model. Now, if you want to make maybe small elements here, you could do this with structure, and then on setup, you have to, yeah, that's why I said it's a little bit hidden. Click on setup and then on mesh control. And global is 2.25, so I will select this surface and maybe do a 1 millimeter. Let me see something, right? 1 millimeter here, and run it once more. Same setup, maybe call it model 2. All right, let's wait a minute. All right, it completed here. Just switch off my phone here. Yeah, and here you see the elements. So if you compare those, you have von Mises stress here, with which is 79 megapascal, and let's jump to the other analysis. So jump over here. You can see 76. So you're getting a little bit more accurate, and you have always to be remembering that those values depend on the mesh size, and only you can only trust them if you do a mesh convergence study. So small element size does not change it anymore. Then it's correct. And yeah, there's some different things as well as yeah, just highly stressed area and just one point which you can neglect. But yeah, this is also more stress engineer torque than CAD engineer. All right, so this is it. And now the optimization part is really not that big of a deal, because you have set already your model, your design space. Yeah, this is what we have done so far. And now you want to optimize it. Here, optimization button, and you can use a model name, whatever, model 3. And there are two common ways of doing a optimization. The one I use the most is maximize stiffness, because it converges a lot better than something which is correlated to stress. So maximize stiffness, and you're giving a % of the initial volume. So you see this dark red color volume, just a fraction of this volume will be used. So you're telling the solver, the optimization solver, well, all right, I give you here maybe 15% of the material. Place it wherever it contributes most to the stiffness. This is the task which the optimization run is up to. So for example, 15 parts. And then the thickness constraint is also very important. This is you defining, well, I have some structural elements here. Well, I just want to have it as minimum thick as, for example, 10 millimeters. And here the automatic value is 6.9. Let's go with 7 because it's a straight number. And also the maximum constraint is, well, I don't want to have clunky areas with a lot of material, because maybe I want to do it as a part which goes into the manufacturing. So word, it's formed by, I have to look it up, sorry about that, a little bit casting. Yeah, casting. It's done by casting. If you're doing a cast a part which is be manufactured by casting, you know about this. You don't want clunky areas where you have lots of material coming all together, because you have, well, not the English word about that, but lunkers, and you know, those things you don't want to have in a casted part. So you can also define something like this, and the automatic value is here 2 times the minimum value. We can play around with that a little bit, but I will just use the minimum, and be aware that this parameter minimum, this is affecting your simulation time quite a bit, because there's more or less this rule that the mesh size should be half or even less than the minimum size. So if you're putting here 1 millimeter, then it will be meshed with 0.5 millimeters, which takes a lot of time and a lot of computer resources. You may not see that here, but it is there, and it will notify you. It will notify you if the solver thinks this run takes more than 50 minutes, right? But I can talk to all of that when it's running, so we don't waste that much time. So now it's running. You can see also here, it's not analysis, but here it's optimization. Here you have also a current folder here, and here you have your files, right? And also see that change a little bit. So sort that by this is the date or timestamp where it's changed, and you can see which is what this is doing here, right? So this is just for you if you're having to troubleshoot a part. So back where was I? We had this thing about thickness constraint. This is one thing. Then we have speed accuracy. Well, here you have the element order again. So more accurate means second order elements. And then you can do all stuff with gravity and contacts and load cases, which you want to have in here. But in this case, it was rather simple because it's just one load case, right? So this works. Now, as the simulation is doing, or the optimization is going here, we could talk a little bit about another different manufacturing constraints. So, as this is a symmetric part, but the mesh certainly is not symmetric, it is a good idea to introduce symmetry. To say, I want this to be symmetric. And another thing is if you want to machine that, for example, from a plate, right? You get a blank steel, want to just laser cut it. Then you maybe want to define the way how material is removed. Those two things I will be covering right now. So let's first look at the design. So this is the design. You see it's not very symmetric, right? But it has a symmetric load case, you could wonder. But one thing is that we did not ask for that. And the other thing is that the mesh is not symmetric. So this is two of maybe more areas where asymmetric things could happen. And it's also not quite accurate because we have not completely symmetric boundary conditions. But all right, you can see that makes sense, right? You can also have here the slider, which, well, basically what you're looking at is a subset of the elements, because be aware that in the result of a topology optimization, all elements are included, always, all elements, all, even those, but with a rather small density. So those elements are not contributing this much to the stiffness of the part, but they are just there. Be aware. So what you're doing here is you're selecting a threshold. Show me all elements which have a density lower than my threshold. So if you set your threshold, really, let me think about that a minute. Lower than? So no, it's higher than. So here's your threshold. You're only showing the elements which have a higher density than your threshold. So here is a rather low threshold. It gets me confusing because you push it to the right, but here you're decreasing the threshold of what you show. So you show more, and as you increase your threshold, you show less, because those are the really, really, really important elements. So you could think of them. Those are the not so much, and those are all elements, right? All right, I hope I got that covered well. Yeah, let's change it back to the design space, and we want to do some different analysis. So we talked about symmetry, right? Symmetry is a part of the shape control, and symmetric conditions. This is this sign. Click here once, symmetric, choose the part. Now you choose which planes you want to use, and we want to have it a symmetry plane here, so this one. So the others we don't want, so we're deselecting those. And so we have just one left, and this is the definition. So on this symmetry plane, it will be symmetric. And the other thing is the shape controls with the draw direction. This means if you have a plate, you want to have it just to be extrudable, you could say, in one direction. So shape controls, select this one, select the part. Then you can have the option single draw. That means you have your manufacturing and taking material just from one direction. And split draw means from two directions. And extrusion means this must be extrudable. And overhang constraint is for 3D printing. So we are doing extrusion and no, I think those two are incompatible. I'm not 100% sure. We will try, but I think those are incompatible. So those two meaning extrusion constraint and symmetry constraint. But let's see. So this is extrusion, and symmetry is defined in the other direction. But let's see. I think this will not work, but we will see about it. Same parameters, maybe a little bit more material. Well, no. Let's go with that one and run it. yeah, here you have it. Unable to apply symmetry and extrusion shape controls. Symmetry and extrusion shape controls cannot be applied on the same design space. Please remove the symmetry or extrusion shape control from the following parts. Alright, what should we go for? I think the symmetry part is rather important, so I will delete this extrusion constraint and run it once more. So same parameters. This is it. Yeah, so what else to talk about here? Well, there's so much things I didn't cover here yet. And I think the video is always also getting a little bit long. Turns to be a whole lecture. Yeah, there's a lot to go into here. We could talk about variables, we could talk about shape optimizations, but I will leave that info all for another video. So this is just doing a little bit topology and showing the main difference between the two versions, right? So this is the thing. Motion we could do, and vector, this pretty much we could do here. That's a good thing. So, well, my feedback I could give to Inspire is a good tool. It's a good tool for a CAD engineer. For sure, a stress engineer would want to go with OptiStruct, but well, OptiStruct in the background, OptiStruct is doing the optimization here. But you cannot influence the model setup, the mesh, this much, and the ways of how you define your contacts or how to define your boundary conditions this much than you can do with OptiStruct or HyperMesh in this case. So it's a good tool for a CAD engineer, it's perfect, and it gives you quick access to a design proposal. And for that case, I think it's a good tool. And I would encourage you, if you have access to the software, definitely use that. You see that I could give you an introduction in half an hour to use it on a basic part, and you could use that on your parts as well. So think about how much you could save if you come up with the good design just from a first starting point. Yeah, don't have to do those time-consuming iterations. You're choosing a radius, it's not enough. Choosing another radius, it's still not enough. Using another approach, another topology, still doing not enough, and stuff like that. It's better to know where to start, and I think Inspire can help you with that. So, and this is my personal opinion about this software or topology optimization as a whole. Well, this looks great, I think. So, right? Okay, now if you want to get this back to your CAD, there's a option here as well. So you could save that as STL, that's always a point, and then model it in your CAD software. But what you could also do is to use the polynerbs here. So polynerbs, and then there is, I think it's fit, yeah, fit. You just choose your volume here, and click on OK, and it will automatically calculate control points which define the surfaces which are the result which you're seeing here right now. So you can see it here, see the mesh here. So this is not FE mesh, this is geometric control points. Then you can edit here something if you want to maybe drag an area or even a line, you can drag that and play around with that a little bit, do a shape optimization with that. So you can do a lot. And also, if you're doing a structure contacts, it will recognize the contacts to your non-designed space area. So you know the partitions we did. So this will get recognized, and then you can just reanalyze this structure as well pretty quickly. Here, I must say, it would be a good idea to always save your model as well, because sometimes I had the experience that with the polymesh it may also terminate your software once in a while. So be better safe than sorry, not like I did here and not saving the whole time. Save the models, and yeah, then you can also delete the models, things you don't need anymore. If you made your design choices, then you're getting not so large files, because right now it saves every simulation into this file. which is on this small model is not a problem, but on your bigger models maybe can also be an issue. And because that's already set, we can do simply as that a analysis here. And then you can compare everything. You can compare your design space, your initial one, mass, and your safety factors, compared to the design with mass and safety factors. In this case, compliance is maybe a thing you want to look at, which is the inverse of stiffness. Stiffness you want to be high, compliance you want to be low. And this is the thing the optimizer optimizes for, right? Oh, intersections found. Part 1 and polynerbs part 1. Yeah, maybe this needs some pre-processing. I'm sorry, I cannot show that here right now. We would have to define the contacts here more clearly and put it here, which I'm not doing in this model, but you can see what this would look like and how you could get back this design. All right, this is about it for this video. Thanks very much for staying around this long, and I hope you have a good one. If you have any questions, just leave a comment, write me an email, and I will be happy to come back and help you out with that. All right, good luck, and if you liked the video, well, you know what to do, and see you.